Bow your heads, please.
Dear Lord Jesus, thank you for this day. Thank you that we can come here and learn about your wonderful creation. And please help us to focus and do some amen.
Amen. Thank you. Do you have your test out? Okay. We're going to run through it quickly so that we can get to everything today. Number one, we were supposed to define our terms, and extracellular digestion was something about it digesting outside of the cells. That's all. Didn't have to be too elaborate, okay? Rhizoid hyphae was the hyphae that was in the mycelium. Did anybody get anything else for that?
I put hyphae inside the food.
Okay, but that's where the mycelium is. So that's just great. Okay. I'm trying to find here. Here we go. I'm going to get back here so I can check myself. Fungi's not my strong suit. Stolon, you should have said something about an aerial hyphae that does asexual reproduction. Could have drawn one, put a little new fungi out there. Fermentation, something about it anaerobically breaking down sugars. Okay. Hyphae itself, just filamentous fungal cells, or you could have put thread-like cells. Did anybody come up with anything else? Okay. Number two, if a fungus forms Hastoria, is it saprophytic or parasitic? You tell me.
Parasitic.
Parasitic in general. You know what bugs me about this? What did we learn about fungus root? Fungus root has a Hastorium, but it's actually a mutualistic relationship. So I kind of have a problem with that, but you answered absolutely correctly. I just want you to know. Number three, what kind of hypha exists in a multicellular fungus?
Rhizoid.
Okay, rhizoid hyphae. Okay. And then let's see. Number four, what does chitin provide for a fungus?
Toughness and flexibility.
You could have said that. I wouldn't have thought of two things because it didn't ask me for two things. So I'd have said structure. Did anybody go that route? You guys are much better than me. Okay. But I'd have accepted that too. Because really it is structure, right? That's what it does. And it doesn't ask for two things. 5, name 2 specialized aerial hyphae. Now here it's asking for at least 2. So you could have mentioned stolon. You could have mentioned, did it ask? Hang on. Nope, name 2 aerial hyphae. Okay, that's what I thought. So you could have mentioned stolon. You could have mentioned sporophore. You could have mentioned sporangiophore. You could have mentioned conidiophore. And then it doesn't ask what it does. So why did they? Oh, you could have said one that absorbs oxygen. That's why. So you could have said that. Okay. Let's see. Number 7. Number 6. I just went right past that one. Number 6. Give the phylum of kingdom fungi. Given the phylum of kingdom fungi, classify fungus with each of these characteristics. Okay, so A, form spores on club-like basidia, that would be Basidia mycota. B, have no known sexual mode of reproduction, that would be Deuteromycota. C, form sexual spores where hyphae fuse, that would be Zygomycota. And D, resemble both protozoa and fungi, that would be Myoxymycota. I'm taking the test as we do it, so if I mess up, you guys let me know, okay? Okay. Number 7, what part of the mushroom holds the basidia? That would be the gills. Is that what you guys put? Good. Number 8, give the means of sexual reproduction and one means of asexual reproduction employed by bread molds, and I'm going to go ahead and read those to you. With the bread molds, the sexual reproduction is when a zygospore is formed. You could have said that the 2 hyphae come together and form a zygospore, but you should have mentioned a zygospore somewhere in there. And then the asexual reproduction, they can use a stolon or they can make a sporophore. Okay, so one of those. Let's see. One means of asexual and one employed. So one of each. All right, making sure. So you didn't have to have all of that. You had to have one sexual and at least one of the asexual. Number 9, name 2 pathogenic fungi and the maladies that they cause. And so you could have gone a bunch of ways. You could have said rusts or smuts. Either one do crop damage. You could have said ergot of rye, which causes death. I like that malady, don't you? Death. Okay, anyway. And then you could have said chestnut blight. You didn't have to say the Latin name. You could have said chestnut blight attacks chestnut trees. That would have worked. You could have said Dutch elm disease attacks elm trees. That would have worked. Or you could have said death to elm trees. Anyway. And you could have said potato wart attacks potato plants. Did anybody here give the Latin names for these things? We bow to you. You are amazing. And you're probably a future scientist, right? Is that the route you think you're going to go, Zach?
Kind of lawyer, but either way, it's still Latin, so.
There you go. Okay, so that works. All right, let's see. So then we go to number 10. A farmer notices that certain crops grow much better in the presence of certain fungi. What is most likely explanation? What's going on there?
Fungus root.
That's right, fungus root. Thank you very much. Number 11. What useful medicine is produced by fungi in genus Penicillium? Penicillin. And what is the general name for those medicines? Antibiotics. And there you go, we're done. Number 12. A biologist looks through a microscope at a single-celled life form. The microscope is not good enough to discern whether the cell is eukaryotic or prokaryotic. We go up to 400 power and you couldn't tell that from our microscope. So, however, the biologist does see that the cell reproduces by budding. What is most likely the kingdom in which the organism belongs? Fungi, that's right. Number 13, why do slime molds appear in kingdom Protista in some biology books?
They resemble protozoa.
Exactly, in their feeding stage. Very good. They resemble protozoa in their feeding stage. Wow, there's no more. I'm turning and there's nothing else there. Okay, so this tells us that there are 4 possible points for each question, but that includes every answer. So number 11, there are 2 answers there, so each one's worth 4 points. Number 9, you should have had 2 answers, and yeah. Hang on, this is really confusing. 13, 14, 15, 16, 17, 18, 19, 20, 21. Just make all the answers worth 4 points, okay? Like A is worth 4, B is worth 4, C is worth 4. Okay, do it that way. Alrighty, we done? Now we get to go on to biochemistry. Aren't you excited? So we're looking at some biochemistry here, and this is important to understand because living things are actually little chemistry factories. That's really what it gets down to. And so we have to understand some chemistry. Now I want to give you the heads up. This is the last easy chapter for a while. Okay. So the next chapter, chapter 6, is where most people get bogged down because the next chapter is cell biology, and we're going to be fine. And the reason we're going to be fine is because I'm a twisted cell biologist. That's what I am. And so I can help you with this. All right, my degree is actually in cell biology, eukaryotic cell biology. I can help you with this. And it's actually quite interesting, but it's where a lot of people get bogged down. So I don't want you to, we're going to get through this together. But I want you to know we've been climbing the mountain and now we're like climbing the hardest part. And once you get over it, it's kind of got a plateau going on there, and then it's going to start going like this. Okay, which is not the same as physical science, is it? Physical science started with the easy part, and then it went to the physics, which for a lot of people was the much harder part. And so it was like, oh, this is going to be fine, and smack, and then woohoo! Okay, this is different than that. We're going to hit the hard part in chapter 6, and then it'll kind of level off, and then it starts going downhill, and it'll get easier. So I just wanted you to know that, okay? So you know how the general tone is. Now, this is the chemistry of life. So we're looking at matter, and we have to remember that matter is anything that has mass and takes up space. So that includes air, and you know that it takes up space because if you blow up a balloon, right? And you know it has mass because it exerts pressure on everything underneath the atmosphere. So even things that we can't see make up matter, anything that has mass and takes up space. What is the basic building block that all matter is made up of?
Atoms.
Atoms, very good. So just like all living things are made up of cells, all matter is made up of atoms. And can anybody actually see an atom? No. Atoms are so small that nobody's ever been able to see one. Now, they can take electron microscope pictures of what they think looks like an atom, but what you learned in the other book was that they really don't know that that's what an atom looks like because there's a couple ifs involved, there's some quantum mechanical math involved, and so it's probably what an atom looks like, but we're not actually sure because they're just too small. And even most molecules are too small to see. And you notice I say most, because when you get into living systems, we get to some huge molecules. And like the DNA molecule, you can actually do an experiment. I think it's in the next chapter, but it may be in this chapter. But one of these chapters has an experiment that you can do at home, and you can extract the DNA from onion cells. We can't do it in here because we don't have the time. But if you do it, you will actually be able to take a toothpick and pull the DNA out of the stuff after and see it hanging because it will be in clumps. Yeah, it's very cool. When I taught at the Christian school system, we did the experiment in class because we had 5 days a week, so we could do it. So it's a very cool experiment if you want to do that at home. But most molecules aren't big enough to see. And then we will look at onion cells. We'll look at the DNA, the chromosomes in onion cells, and each of those chromosomes at 400 power, you can see them, and each of those chromosomes are actually a huge DNA molecule, and that's what you're looking at. So most of them are too small to see, though. So cells are the building blocks of life. Atoms are the building blocks of matter. And we're told here that there's approximately 1 billion atoms in the dot of an eye, to give you a little scale. So, and then, I don't know about you, but most of us can't get our head around what's a billion. Well, if you stood here and dropped a $20 bill every second for over 100 years, you'd hit 1 billion. It's a big number. It's a really big number. And so atoms are really, really small. That's what I guess I'm telling you. I'll tell you what, turn to page 1, I think it's 126. Yeah, it is. 126. On page 126, you have the schematic of a helium atom. And once again, if you took physical science, you learned the Bohr model of the atom, where in the nucleus you have nuclear particles that are positive and neutral. What are the positive particles called in the nucleus?
Protons.
Protons. And what are the neutral particles in the nucleus?
Neutrons.
Neutrons. And then way out there circulating in outer space somewhere are the little negatively charged particles called electrons. Very good. And remember, we said that if we put a marble at home plate in a baseball stadium, that the first electron would be at the outside edge of a professional-sized baseball stadium, and that's where the first electron would be. And that's a regular marble. If we up that to a shooter marble, the first electron would basically be from here to the interstate, okay? Now, what does that mean? That most matter is made up of mostly empty space. That explains a lot about a lot of people, doesn't it? But we won't go there. Don't repeat that. So most matter is made up of mostly empty space. Now, I don't know you, but I immediately go, well, wait a minute. If matter is mostly empty space, then why can't I put my hand through it? Right? And it's because those electrons are whirling around the nucleus of the atom, and they are negatively charged, and the electrons in the book or the podium are also negatively charged and whirling around the nucleus of that atom. So it literally makes a force field because the two negative charges repel one another, and so it makes a force field. The reason you and I can put our hand through water is because those molecules are actually not all up next to each other, but they're actually dancing around, and so because they're dancing around, you can put your hand through it, you can pour it, and it'll take the shape of the container. Remember that? Kinetic theory of matter? And then remember... And then remember, she just had lunch, she's ready. And then remember that if we're looking at water, actually, we've got the in the solids, we've got the dancing molecules in the liquids, and then if you continue to add energy to it, boing, 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 bouncing off the walls, and you turn it into a gas, take the energy away, it comes back down to the dancing, take more energy away, again. Okay, so those are your phases. And so we have to know the Bohr model, and he tells us here, Bohr, B-O-H-R, named for Niels Bohr. It is not the model that we actually hold to currently. Jacob knows that because Jacob's actually in chemistry also, because he's a crazy man. We actually now believe the quantum mechanical model, but the Bohr model works really well to just draw these things, and it gives us something good to work with, so that's what we're going to use. Okay? And so depending on which atom, and this book is probably the only book that doesn't have a periodic chart. We're going to try this. Oh, hold it. How's that? Okay. Now, we're only going to use this. Okay. The periodic chart is set up such that the atomic number actually tells us how many protons it has. And any atom that only has one proton will also only have one electron. And if it has one proton and therefore one electron, it will be a hydrogen. And hydrogen acts a certain way. It is a colorless, odorless gas that is explosive. If you manage to kick the tree. If you manage to get this is good. If you have 6 protons and also 6 electrons, then you end up with a black, crumbly nonmetal that is carbon. Okay, if it has 6 protons, which means it also has 6 electrons, because remember it'll have equal numbers of protons and electrons, because atoms by definition are electrically neutral, so they will have to have the same number of protons and electrons. Therefore, then it will be a carbon. But as soon as you give it one more proton, and now it has 7 protons and 7 electrons, now it is no longer a black crumbly solid. Now it's a colorless, odorless, inert gas called nitrogen. Yeah. Does God have a Lego set or what? Right? I mean, one little change and you got something totally different. And then you add one more proton. Well, yeah, it's still a colorless, odorless gas, but this is not inert. This is what causes all combustion to occur. I mean, it's Fire City, right? And so very different depending on how many protons it has and therefore how many electrons it has. Now, if you've ever wondered why this chart is set up in the strange shape that it is, part of it has to do with where the electrons are. You've probably already noticed that it goes 1, 2, 3, 4, so it builds as far as how many protons it has and therefore how many electrons it has. But the strange shape to this chart is actually to show you that all of these guys actually have one electron on the outside edge and they want to give it away. And all these guys have 2 electrons on the outside edge and they won't give 2 away. Now the only reason I mention this is this. Your book told you that the number of electrons determines the chemical characteristics of an atom. And that is true. This is actually organized as to how many electrons they have and where they are located. Isn't it, Jacob? He just had a test on that, and he's painfully aware of that. So it really is important where these electrons are, and that's why the chart is actually set up that way. Now, another thing that you learn is helium, which is way over there, and it's 2, right? We learned that helium has 2 protons and 2 electrons, but what can vary within a helium atom and it still be a helium? Yes?
The neutron.
Good. The number of neutrons. So helium, all heliums have 2 protons, but some heliums, and they all have 2 electrons, right? They have to have those. Obviously not to scale. But they can have differing numbers of neutrons. So there can be a helium with 1 neutron, there can be a helium with 2 neutrons, and there can be a helium with 3 neutrons. And it doesn't tell you in this book, but for those of you that have had physical science, you remember that these are called isotopes. They're isotopes of one another. They are all within the element of helium because they have the same number of protons and therefore the same number of electrons, and therefore they have the same chemical characteristics. They just have different masses. How we name a particular atom within an element. So one of your vocabulary words on page 126 was model, and it gives us a representation of something we cannot see. And we cannot see an atom, and so we draw the Bohr model to give us something that we can get our head around. That's really what it gets down to. And then over on page 128, you are given the definition of an element as a collection of atoms that are all made of the same number of protons. But once again, they can have differing numbers of neutrons. So if they're within an element, all heliums are going to have 2 protons. How would we distinguish a particular atom within the element? We would give its mass number. And so we would say that this is helium, and we would determine its mass by adding up these particles in the nucleus. That's what gives it its mass. I'm going to tell you that because the electron is 2,000 times less massive than a proton or a neutron, and therefore it's so small that it just kind of falls out of the picture, mass-wise, okay? That's not in your book, but now you know why they just ignore them. They're just looking at these particles for the mass. That's why. And so, how many particles are in the nucleus of this one? 3, right? Can you guys read that? 3? Okay. And so this would be called helium-3. So what would this atom's name be?
4.
Helium-4. Now, so that I don't have to keep writing this out this way, I love it. In Jay Wiles' new chemistry book, he keeps saying how lazy chemists are. And I think that's so cute because we all are basically lazy, right? And so we come up with chemical symbols for this. So we don't want to write out helium-3. So we use the chemical symbol for helium, which is either going to be a 1 capital letter or 1 capital letter and 1 lowercase letter. And so we would write out the helium symbol, and then we put the 3 up here to the top left. Now you might wonder, why in tarnation would they put the 3 up there to the top left? Well, because if you put it over here, it represents a charge that an atom develops when it turns into an ion. And if you put it down here, that represents how many of them are in a particular molecule. So the space is taken on the right-hand side of the symbol. So you got to go up to the top left. And that's where they put it. So this, and this one's supposed to be 4, isn't it? Because that's 4. I was just writing that one. So this is supposed to be helium-4. And so that's the shorthand version for that. And remember that the symbols are from the name at the time that they came up with the symbols. And at that time, there were a lot of English names given because England had colonies all over the planet at the time. The sun never set on the British Empire at that time. So there were a lot of British or English-speaking scientists. But if you weren't an English-speaking scientist and you discovered an element, you gave it a Latin name. If you were Russian, if you were French, if you were Spanish, you gave it a Latin name. And so that's why a lot of the names were Latin at the time, when actually Berzelius in the mid-1800s was the one that came up with the idea of symbols, because he got sick of writing out all this stuff, and I don't blame him. And so he said, let's give it, the first letter of its name, and if it's already used, we use the first letter and a second one, and that's why helium is He, because hydrogen got H. And whatever their name was at the time, that's the symbol. And so sodium got Na. What's up with that? Well, because its Latin name is natrium, and potassium got K. Well, but its Latin name is catrium or something like that, and iron is Fe because its Latin name is ferrous. And so some of them are Latin. Aren't you glad you don't speak Japanese or Russian or something? Because then none of them would make any sense. But at least some of them look normal, right? That's about half. Yay! So, okay, we're told that the only ones you have to be familiar with are up on page 129. That carbon is C, hydrogen's H, oxygen's O, nitrogen's N, phosphorus is P, and sulfur is S. Wow, that's too easy. They all look so normal, don't they? Now, we were supposed to answer some questions, so let's go back over to 128. And on the On Your Owns, 5.1, the Bohr model of the atom is sometimes called the planetary model of the atom. Somebody on this side of the room tell me, why do they call that the planetary model? And if you're not sure, flip back a page and look at the Bohr model. Why might they call that the planetary model?
Because it has a center and an orbit.
Very good. It has a center and stuff orbiting around that center, just like the sun would be in the center and then the planets would orbit around it. Very good. Thank you very much. Okay. Let's see. Number 5.2. What determines all of the atom's properties? I find this a very conflicted, ambiguous question. Okay? What determines all of the atom's properties And so they want you to put the protons, neutrons, and electron. What determines the vast majority of the atom's properties?
Electrons.
Yeah, I don't know. See, you got that. I immediately read that and go, didn't you just ask that question? Come on, how many of you thought that? Didn't you just ask that question? Why are you asking it again? He got it. You see that? Okay, that's the attorney in him. He's going to be good. All right, 5.3. The atom has 13 electrons. How many protons does it have? 13. Remember, those two actually have to equal one another so that they cancel each other out as far as the charge. That's by definition, an atom has to be neutral. We already talked about elements. And so go over to page 130. And let's look at the on your own there. 5.4, two atoms have slightly different properties, but they belong to the same element. What is different about them? Christian, good, neutrons. Just say it out loud then, that's great, thank you. And 5.5, the element carbon is composed of all atoms that have 6 protons. One of the atoms in the element carbon is carbon 13. How many protons, neutrons, and electrons are in a carbon 13 atom? Well, first off, how many protons are there? 6, because they already told us that. How many electrons do there have to be? 6. And then how many neutrons are there? 7, because we would take the 13 and subtract the atomic number from it, the number of protons, which 13 minus 6 is 7. I can do this. And so that's how you would determine the number of particles in them. Now, those of you that took physical science with Apologia, you've done all this before. So you probably don't remember it because that's the kind of thing you don't want to remember. But you've seen this kind of stuff before. Then we get into molecules. Whenever you link 2 or more atoms together, you have a molecule. Now, it doesn't have to be something new. It can be 2 of the same atom, and if they're linked together, you have a molecule. In chemistry today, they just learned about things called homonuclear diatomics. In the atmosphere, the oxygen we breathe is actually, those lines represent a shared pair of electrons. It's O2. It's not just oxygen that we breathe. We breathe an oxygen molecule where 2 of those are attached together. When we exhale carbon dioxide, right? And that's a molecule because when 2 or more atoms are attached together, you have a molecule, whether they're the same thing or not. As soon as 2 or more atoms are attached together, you have a molecule. Now, interestingly, we cannot live without oxygen. It is absolutely essential to us to survive. Yet, if I add 1 more oxygen to this and make it ozone, now it's absolutely deadly for us. It's a totally new situation. Got another one for you. Iron is a very hard substance that tends to be magnetic. Okay? Attach an oxygen to it, and you get iron oxide. That's rust. It is no longer strong, and it's no longer magnetic. It's a brand new molecule. Brand new molecule. So even one change of 1 atom in a molecule gives you a brand new molecule with brand new characteristic properties. Like I said, does God have a Lego set or what? Okay, so he can do all sorts of interesting things. Now, when we look at these molecules, we want to show the chemical formula. And once again, carbon dioxide would be represented structurally like this. And so we would write this as CO2. Notice there is no number here. That is because the invisible one works in science as well as in algebra. Remember the invisible one? There's a 1 out here, there's a 1 under here, the invisible one. Well, the invisible one strikes again, he's there, okay? So I say this because on your test, you're going to have to count the atoms in a molecule, and frequently I see the students count everything right and then forget to count the one that didn't have a subscript. Don't forget to count the one that's not there, the little 1, okay? So how many carbons are in this? Now it's real obvious here, but if you can look at this, how many carbons? 1. How many oxygens? 2. Very good. How many carbons in that one?
1.
How many hydrogens are in it?
3.
How many oxygens are in it? 1. So how many total atoms are in this molecule? 5. Very good. So you have to be able to distinguish from the chemical formula how many atoms are in these given molecules. Okay? Let's see. And he gives us, okay, carbon monoxide, which is CO, carbon dioxide, CO2. You guys are familiar with that, right? Carbon dioxide is what we exhale. Carbon monoxide is absolutely deadly poisonous to us. One little change. It's because our red blood cells pick this up thinking it's OO, that it's O2. So our red blood cells pick it up as if it's O2, but they can't shake it loose. And so then they're dead. They go around and around in your system, but they can't dump any oxygen. They can't pick up any carbon dioxide or water vapor. They can't carry any nutrients. And so it just like destroys those red blood cells. And if they don't find you soon enough, you're dead. They can't give you a transfusion to put new red blood cells in your body. So it's very, very dangerous. Carbon monoxide poisoning is very, very dangerous. Here in Florida, we don't deal with a lot of that, but places where it's cold in the wintertime, it's a danger, like when they start their car in the garage because it's too cold to go outside, you can get carbon monoxide poison real easily. Also, fireplaces can produce a lot of carbon monoxide. You know all the black stuff you see on the fireplaces? That shows you there's incomplete combustion going on because that's gone straight to soot, which is just the carbon. So it's also producing carbon monoxide. So when you see that, you guys need to know that you need to add air to that situation so you're not going to get carbon monoxide poisoning. Because we're all dumb Floridians. We'll sit around going, isn't that fire pretty? You know, we'll just sit there, we'll get poisoned, it won't be good. Anyway, so, okay. See if there's anything else there we need to do. So let's look on the bottom of page 131. We have identified each of the following as either an atom, an element, or a molecule. When it says atom, remember when we name a specific atom, we give not only the element, but we also give the mass number. That tells us it's the specific atom within the element, okay? So the first one, A, NH3, is that an atom, an element, or a molecule? Molecule, because you have more than one atom there, therefore that's a molecule. How about on B, we have just P for phosphorus.
Element.
That's an element because it doesn't distinguish with the mass number. It strictly gives you the symbol, therefore that is an element. How about C for carbon-14? That's a specific atom within the element carbon, isn't it? Very good. How about S? D is S. Element. That's an element because it's all of the different sulfurs and there's different isotopes there, but that's just giving the general sulfur. And then E is P4. So how about that one?
Molecule.
That's a molecule because you have more than one there. We know that because the little subscript 4 tells you have 4 of them attached to one another. All right, 5.7. A student is told to study the chemicals nitrogen monoxide and nitrogen dioxide to determine their differences. The student reports back that there are no differences between the molecules because they are both made up of the same element. Is the student right or wrong?
Wrong.
Wrong. And does anybody want to try to tell me why? Yes, sir?
Well, the problem with that is that despite the fact they're made up of the same element, that even one change to a molecule can drastically alter the properties of it.
Very good. So as soon as you have any changes at all from one molecule to another, you have brand new, unique characteristic properties. Brand spanking new. Okay. And that is the case. Thank you. And then 5.8, name each element and the number of atoms of that element in one molecule of acetic acid, C2H4O2, which is the active ingredient in vinegar. And so all of you tell me, how many carbons are there?
2.
How many hydrogens?
4.
And how many oxygens?
2.
Very good. Okay, so that's what you have to be able to do there. On page 132, we get to changes in matter. And we have physical changes, and then we have chemical changes. And as you probably have figured out, The first module of this book, we spent the whole module laying down vocabulary words and basics so that we could apply those as we went through the course. Now we are laying down the basics of biochemistry so that we can get into cell biology, genetics, respiration, all sorts of really interesting things. But we have to have these foundations in place. So that's why we're just going through and kind of building these things right now, okay? Physical change versus chemical change. Now, we're told that a physical change is a change that affects the appearance, but not the chemical makeup of a substance, whereas a chemical change alters the makeup of the elements or molecules of a substance. In other words, a chemical change changes the identity of what it is. A physical change does not. So if we take H2O, which I know everybody knows what that is, and we put it in the freezer and we freeze it into a solid, or we take it out of the freezer, put that ice cube into a pot and we boil it away and it goes away as a gas, have we changed the identity? No, it was still H2O all along, wasn't it? Whether it's ice, a liquid, or a gas, it's still H2O, no matter what we're doing there with it. We have not changed the identity. And we can go back and forth between them, can't we? It's reversible. Whereas if we put flour and water and honey and an egg and mix it all up and throw it in the oven and cook it, do we have a chemical change or a physical change?
Chemical.
We have a chemical change, because can you get your egg back? You have definitely done something to change the molecular structure of that. And frequently, there'll be energy involved when there's a chemical change, whether you're putting it into the system or whether it's giving off the energy. There'll usually be some kind of energy exchange there. But you change the identity, and the book gives a really good example. If I take a piece of paper and I tear the piece of paper, is that a chemical or a physical change?
Physical.
Physical change. But if I take the piece of paper and I light a match to it, is that giving me a chemical or a physical change? Chemical. Can I get the paper back? Have I changed the molecular structure? Oh yeah. I took the paper and I turned it into ash and carbon dioxide and water vapor. Can't get it back. That was a chemical change. One that you guys have done when you were in physical science is you took water with Epsom salts in a cup and you put a battery down in it, and you did electrolysis where you split the water molecules into hydrogen gas and oxygen gas. Was that a chemical change or a physical change? Chemical change. You actually took H2O and you turned it into H2 and O2, right? You broke down the water molecules. So that would be a chemical change, okay? Can everybody kind of get a grip on the difference there? Good. All right, so on the top of page 133, 5.9, it says, identify the following changes as chemical or physical. Putting milk on cereal.
Physical.
Yeah, that's physical. Most of us would think, no, you can't get that cereal back, but you really can. You put it in a dehydrator or something, you really can. Won't taste the same because the sugar will be washed off, but that's all good. All right, how about baking bread? Chemical. How about boiling salt water?
Physical.
That's a physical change. You can actually get the salt back out. Just like if you put, let's say Crystal Light or something, and you made, lemonade, something like that, you can actually get that back. You can boil off the water and get it back. So that's a physical change, not a chemical change. It's just dissolved in there. That's not a chemical change. To dissolve something isn't a chemical change. And you read about that. You know a little bit about that. So then we get to physical changes, and then we'll come back to chemical changes. Physical changes include phase changes, which we already talked about. And a phase change is where you have something, it's a difference in the energy level. It says there, one of three forms, solid, liquid, or gas, which every substance is capable of attaining. It's just a lot of them don't attain those differences where in the temperature range that we can observe them. Like oxygen is a gas at normal temperature, but if you make it cold enough, you can actually make it a liquid. And it's got to be kept under pressure and really, really cold. Same is true with liquid nitrogen. Matter of fact, it's absolutely dangerous because it has to be so cold to be liquid nitrogen. That's what they freeze cells back in when they're cloning cells. I used to work in cancer research, and when we would get a cell line that was doing what we wanted to, and we would clone that cell line, and then we would freeze them back to try to keep them, we would put them in liquid nitrogen, and that stuff is very, very dangerous. And I just want you to know, so that you're aware, we did all that, and like 1 out of every billion cells would come back viable after freezing them down. And the reason I say that is because these sci-fi movies that try to tell you they're going to freeze you and then bring you back later when they figure out, ain't no way. 1 in every billion cells is going to come back. There's not going to be enough of you left over to do. So just so you know, okay? Just so you know. Anyway, we already talked about that the solids have the least energy, therefore they're cold, and that if you add energy to them, then they start dancing around and they become liquids, and they take up more space usually, not the case with water, but with everything else basically. And then if you add more energy, bing, 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 bouncing off the walls, and you turn into a gas. Take away some of the energy, goes back to dancing around. Take away more of the energy, goes back to ice again. And in general, the more energy you add, the more space it takes up. Water is an enigma, remember, and it's because of hydrogen bonding, and they're holding hands, and they're line dancing, and that's why to freeze water, it actually drops the hands, moves apart, breaks those hydrogen bonds, moves apart, and that's why ice floats. It's less dense, takes up more space, and therefore it floats on top of the liquid. But it is the exception, not the rule. Most things, if you freeze them and you drop them into the liquid version of what they are, thump, right to the bottom. Okay? You can always try it with butter at home, but that gets very pricey. Okay, so over on the top of page 134, it tells us that another physical change that we can do to things is you can dissolve it. And I already mentioned that. If you take the Crystal Light or Weiler's lemonade powder and you dump it into the water and you stir it up, you can make it taste like lemonade, but you can actually boil off the water and get back the powder, which is weird, but it's true. And the same way with salt. If you dissolve salt in water and you stir it up and it dissolves, it disappears, and then you boil it off, you can get the salt back. If we do dissolve something into something else, we have what's called a solution. The bigger part, the thing that's doing the dissolving, is called the solvent, and the thing that's being dissolved is called the solute. Now, those of you that know me, I've told you this before, but for those of you that don't, I get very confused when things are very close together.